Good morning. Today we are going to talk about trust aware routing. The threat model basically looks into the components where two parties want to talk, both of them are trustworthy, they are good people in the society, but it is just that they cannot directly talk, they have to talk through, no matter how they talk, whatever routing protocol, it needs to go through the territory where things are potentially untrusted. Then question is, how do these people communicate and keeps the communication safe, secure, authentic during the communication? Is there any way? Of course, this question is invalid if there is no possible path. If there is a path, can you find the path? In fact, the real question is which path is the least troubling. You have to go through the forest from point A to point B, which forest do you cross through and your chances of survival is highest. So, that is really the problem of trust aware routing. So, what we try to do, so this basically what solution do you kind of talk about, and low performance, and the bigger problem is in many of these cases, if you think of Trojan, if you think of something else, they may not be fully malicious all the time. If that they are fully malicious, we know by definition there is no path exists, you cannot communicate. Then somebody who is intermittently malicious, sometimes they will look blue, sometimes they will look orange. So, in that kind of situation, how and what you communicate. And there are a lot of work, as I said, in the classical computing domain, and there are also different related works, and we are trying to make it lightweight. So, the way lightweight work works is basically, so when you meet with strangers, when I hire a PhD student or anything you do, you have to deal with such situation all the time. What do I do when I hire somebody, a PhD student? We send an email to the professor who taught the course. Either that name I get from the application itself, or I just try to figure out which university, oh I know that university, Dr. Korfa. So, you kind of have the word of mouth and you rely on it. And so, then therefore, if I am A, I am trying to talk to B, either directly, if previously I never encountered with B, I have no clue. But if I was hurt, offended, cheated, then I know how to deal with B or whether to deal at all. What about C? For C, I never spoke with C, but B did. So, then I want to get the view of from the B or whatever the trust B says. Now, if B says, oh C is wonderful, how much do I trust B's opinion? Then you multiply by that. So, that is basically the basic idea. So, A is confident that B is trustworthy, that is like 1. Then A is confident B is malicious, that is like -1. Again the numbers you can change, that is like, and A has no idea about B, that is like 0. So, we are trying to assign some trust values, so that we try to compute in the routing protocol, we kind of do some kind of computation. So, we came up with bunch of equations following some ideas and theories, that is not important, but basically trust is updated depending on successful or unsuccessful transmission. Remember in the mesh network I talked about, when you are communicating with somebody and some packets are delivered perfectly fine, some packet came back, oh that has not been delivered, you have to retransmit. How many times you have to retransmit? But again remember, you A would always send to B, but it might not be B's problem why the retransmission is happening. But still you will kind of, through this equation you are going to penalize the B, because maybe somebody else in the path is actually causing the congestion, and it seems like every time I send a request, that wherever the things responded me I did not get it, you have to send it second time, third time. So, then you are kind of having little not so pleasant feeling about B. And in different types of protocol like XY protocol, XY routing protocol, you follow only one path, but in this particular story we are going to follow different paths, because if you have a fixed path you really do not have a choice, you have to send through them. So, trust aware routing basically uses different type of path, and the key idea of all these equations is basically either it is a direct trust or it is a delegated trust. Do I believe the word, and how do we propagate the trust? That is basically the one. So, destination router in same row same column forward to neighbor along that row column towards destination, some trust values of different paths toward destination and pick the path with the largest value. So, that is the key simple idea, simple heuristic. And what you really want to then look at. So, there are multiple things you look at when you are kind of evaluating. Of course, the typical thing is kind of network on chip delay and execution time, which should kind of reflect, does not need to be, and then number of packets you injected and how many of those packets actually delivered. So, when you model this and evaluate this, you have to make one of the node malicious, they are just sitting there and just destroying the packets, not forwarding it. Again, what threat model you impose, here what we imposed is basically just throwing in the dustbin. A packet coming in, it is supposed to forward, it is not forwarding it, it is just throwing in the dustbin. In this kind of model, how much of performance penalty, what packet injected, and you kind of compare. So, in basically this particular work, we also looked at different other comparisons with real benchmark, those were and with synthetic traffic pattern, and comparing with without malicious. If there is no malicious at all, then what should have been the performance, and with malicious and so on and so forth. And we are basically have to show that in real as well as synthetic benchmark, with your solution, you if there is a path, you can find such a path and your overhead is not too much. That is basically the objective, and how much less energy, area overhead, all those are important. Any question on trust aware routing? Because you still have to communicate, you are trying to find a path if exists, and initially you are expected to make mistakes. The next one I am going to talk about is digital watermarking. So, you probably know what watermarking is. Here we are doing watermarking for authentication. In pictures we have watermarking, and we did all of that. So, basically this watermark, we are going to encoding can use packet content or timing also. How we do? You put the watermark and then it goes through the network on chip, and on the side you extract the watermark and check. Now, the question is, why are you doing this watermarking? How do you do authentication normally, if you recall? Any kind of digital signature like ECDSA, or which uses indirectly SHA or hashing, those are extremely expensive to implement in the network on chip. So, it basically it significantly reduces the expense of authentication. Of course, I am not going to show you the theoretical analysis, which I did not show even for the incremental encryption, that when you do that how much security strength goes down. Because in block cipher, one of the classical disadvantage of block cipher, you are breaking into block and you are doing, if you think about it for a moment, if you are breaking into block and reducing the size, you cannot use 128 or 256 bit key anymore. It does not make sense XORing it with bunch of zeros padded. So, the moment you reduce that, then your complexity, let us say you are making 16 bit blocks and your key size is 16, 2 to the power 16, anybody can do brute force. So, that is why there are some more stuff that needs to be done for you to give some theoretical guarantee. Same thing for watermark. If you say, oh, I will use watermark for authentication, I do not want to implement elliptic curve, the digital signature algorithm, that is so expensive. But then you have to compare what was the security strength of ECDSA and what is the security strength of this. Is it easily breakable? What is the catch? You have to just say that. So, this watermarking basically idea, then the way is basically when you are sending the data, whether then any malicious component is trying to take that data out through eavesdropping, right, or it is trying to pose as somebody else. So, it is a tag based authentication, and in the tag based authentication, the way we are doing the authentication, when you are looking at different time step and the packets are going in, you are basically kind of figuring out the inter packet delay. The delay between different packets, you are trying to figure that out, and once you have the inter packet delay, then that delay itself you are encoding as a watermark, right. If you recall in the PAF, the process variation is itself you are using as a watermark. Here the inter packet delay. Now, if you are an attacker, you can always come up with a synthetic benchmark. If you know what inter packet delay got created in a particular benchmark, you can always create it. But if it is a real benchmark, every benchmark, the way packets or the inter packet delay has a unique footprint. That is what that statistics I did not show, it has a unique footprint. The delay between different packets, the way packets are going, how many sub packets are getting created, and the injection rate, propagation rate, delivery rate, if you look at, they have a unique footprint. In fact, when we talk about machine learning today in the afternoon, you will see machine learning implicitly, explicitly basically figures all this out. It is just that we did this research first, then the machine learning research. If we did not do this research, then explainable AI would have told you what it is trying to do and why it is finding certain patterns. Now, in layman terms, I wanted to break it down in layman terms, all these equations. What we are trying to do, if you look at the inter packet delay for any program, it is going to follow some form of uniform distribution. So, there would be lot of packets with hardly any delay between them, think of 0 delay. So, there would be lot of them, and then the other ones are kind of spiked out. So, which is not as beautiful as this, in reality it is kind of this. So, but it still kind of fits the kind of nice uniform distribution, right. And then what we are trying to do, so we want to shift this by certain amount. Think of you introducing some extra delay in a predictable manner, and then you shift it. So, somebody shifted is actually 1, somebody not shifted is 0. So, that is kind of the notion, and we use that as a watermark. So, once you do that, then some more equations are not important. So, then you want to just kind of do the comparison. Again you look at, if you do that, all these stuff, shifting, delaying, how much does it affect the thing? It does. So, for example, default network on chip, and these are in, so it is like 0.4 to 0.6 or about things. So, it is like close to 20% overhead, but if you compare to the authenticated encryption, any of the authenticated encryption you already know about, then it is going to be between 40 and 1. So, it is like almost 60% overhead. So, that is the thing. If you want to implement a security mechanism, it is not going to be for free. So, you get some security, you have to pay something. As a designer, you have to make a decision, are you willing to pay that cost or not. And same thing for execution time, overall execution time for some of the benchmarks, for real benchmarks, and the execution time difference similarly, I probably summarized it. So, authentication would take 57% overhead, whereas watermarking will take only 26% overhead, and delay also have a similar kind of footprint. Any of you have any question on digital watermarking? So, if you want to pursue a research on this line or similar to this, your core objective still remains the same. We want to enable authentication, somebody talking to somebody, can we maintain that information? Here we are maintaining that information, who is talking to somebody, or if somebody is saying I am A, this is my message to B, how do I know it is actually A? So, that signature is encoded as the inter packet delay, that is how it is. Now, we are going to introduce another concept called chaffing and winnowing for encryption, but before I do that, let us look at the threat model. So, another thing I forgot to mention, in security community, anytime you publish a paper, there has to be an explicit section on threat model. What is the threat? What is the vulnerability? What are you trying to solve? If the community or reviewer think that threat model does not sound reasonable or realistic, that sounds fake, it does not matter what you have in the paper, it is all rejected. So, here threat model is somebody, a source is trying to talk a destination, some node, right, it is trying to send the packet, and an adversary trying to eavesdrop. So, this is basically, think of an eavesdropping attack. We are trying to implement an encryption technique, but it is a lightweight encryption technique. We could have used AES, RSA, any of those, we are using a lightweight solution, right. So, adversary, so encryption will happen here, and once encrypted packet flies through, even if adversary tries to consume, it will not be able to figure out anything, because it does not have the key. Any question on this threat model? This is basically eavesdropping attack, right. So, what is the solution we are trying to do? It is motivated by seeing what happens in my village, which is when you have a set of grain, whether it is rice or paddy, whatever it is, you use the air, normal air. These days they use some fan, they have electricity. Earlier they used to use the air, and on the fan, so that the husks will the chaff will go away and the wheat or rice will fall down. You just separate them out. So, this is called adding, this is called chaffing. You add the garbage, and this is called winnowing, you get rid of it. So, that is the key idea, and we will do that on chip network. Any of you have the question on what is chaffing and winnowing means? Winnowing, you separate the good from bad, and chaffing is you add bad things to good things, right. So, why do you want to do that? How does that help? Before that, I want to show you an animation. So, let us say this is the message the Alice want to send to Bob, right. This is source, Bob is destination, we want to send this message. Then we break that message in few parts, that is the, think of that is the packet, 64-bit blocks, and then we have in reality, if you do before chaffing and winnowing, this is what happens. You do the break it in parts, and of course, in the parts there is no English sentence, it is all zeros and ones corresponding ASCII characters. You put message ID, you put message authentication code. Remember SHA with HMAC, hash based message authentication code, you put message authentication code, and what we are doing, we are putting some garbage in it, chaff, we are putting some chaff in it, we are putting some message ID, some fake MAC and all that stuff we are putting in. And how would that help? Because if I do that, now when message would be sent, the green ones are actual message, the red ones are the fake ones. Remember that red sentence we had? So, when that happens and it goes to Bob, Bob is able to kind of figure out what it is, but the whoever is eavesdropper has no clue how to separate those chaff from the original one. So, the question is, can we, this is exactly what we want to do. We add some chaff, other people will not know. And when this idea came to us or thought about us, first thing occurred to us, nah, it is not going to happen. Can anybody tell me why this is not doable in the first thought, or what is the problem with it? Network has already problem, resource constraint. You are putting some more garbage on it, you are going to slow down the average network latency will go up, the execution time will go up. How is that a good idea? That is never a great idea, right. So, but the way we kind of implemented, that is another animation. So, the way we implemented is the following. So, then think of this message we divided in 3 parts, and everybody is trying to steal, and then what we did is one of the packet I do not want to send through that path. One of the packets I will use a different route that Eve has no access to, and all these 3 packets will get combined. Alice will exactly know what I sent, Eve will have a total wrong view of the message. Eve is seeing purple, but actual black was sent, Alice is getting the right message. The question is, how do I achieve this? The way we achieve this idea of encryption, if you get all the packet, you actually get the message, otherwise you do not. This is known as, I will introduce that, this is known as all or nothing transform. Again, these mathematics I am not going to introduce. This idea is, if you do not get all the packets, you are not going to know what the content is. Think of this as a weird encryption technique, all or none. Once you have this technology all or nothing transform, on top of it, so this picture this says if you get all of them, then you know it. On top of it, we are putting this chaffing and winnowing on only one block. Think about it, I take the whole message divided into lot of blocks, only one block actually I encrypt, and that too, that encryption is through chaffing and winnowing, only one block. Other blocks, I mean it may seem silly, other block we keep as it is. So, just the analogy is actually wrong. Let us say I wanted to send a message, I love you, and then I and you can see, this word you cannot see, Now, that is not exactly what is happening. All or nothing transform has a security guarantees and fundamental stuff, and how, what is the idea of new, this the physical idea of new channel is nothing but one of the packet I am encrypting. So, that is the visual illustration of going through another path, is actually not going through another path, it is just that one of the packet I encrypted. So, in this picture it seems like Eve is not getting which one, the green one, but in our life green one is also going through it, but it is just that green one is encrypted, and because green one encrypted, Eve cannot figure it out. So, therefore, it cannot figure out the whole message right there. Any questions? That is basically the key idea. And how do we do that? Let us say this is your message. By the way, this message breaking up packet, this is for any network, not just network on chip, even the general purpose network. This is the idea. You take a message, divide into blocks, and those block, we are taking one block. Now, you can take more block, that is fine. You take one block, and then we are trying to put the kind of each of the block, the wheat part is actually the main information part, important part, real part, and the chaff part is basically some garbage. So, this basically in the wheat part you may have say data bit, counter, message authentication code and all that stuff, actual message itself, and then the chaffing part is basically the garbage we are adding. That is basically what we are trying to do, but it builds on the guarantees of all or nothing transform. The details I am omitting, but it was not the example I took, I love you, and I and you part you can see it like a clean text, it is not that. So, actual, as I said, actual computation is really intense. On the sender side, we kind of do all or nothing transform, even computing all or nothing transform, that itself is resource intensive. So, we kind of took some ideas from quasi group, from mathematics, and tried to do that. Even the MAC computation, the message authentication code, that is also intensive. We kind of tried to do pre-computing this thing, and how do we add the chaff. Same thing on the other side is exactly opposite, pre-computed MAC tags, winnowing, removing the chaff, doing the inverse all or nothing transform, which is again in the we operate on the quasi group, and we basically get the message. And so, then we kind of run on real benchmark, and typically in on chip network domain there are two benchmarks that are widely used, the splash2 and the parsec, and they also support parallel multiple benchmarks are running on the multiple core at the same time. And the kind of story then I wanted to show you is that if you do not do anything, if you do not have any encryption, you are just sending the data as it is, then execution time is the inverse of kind of performance. So, then basically you will have really faster execution time, right, it takes less time to execute a program, that is a good thing. If you are putting, for example, AES with full encryption, we are giving advantage AES of parallel counter based counter mode, then it is going to take that much of time. This winnowing and chaffing basically gives you a reconfigurable security option. So, what that basically means that you are able to choose how much security strength you want, whatever guarantees I did not talk about, and how much overhead you are willing to put. If you keep going the number of chaffing and winnowing bits, how many bits you want to add, if it goes too far, it might take actually more than if you just implement using AES. That is not a good, performance penalty might be too much, but it has one more advantage. So, by the way, this is the packet latency or average how long each packet takes in the space, and this one is total execution time. So, technically speaking, we are using somewhere around 64 bits. So, technically performance improvement wise, this solution actually not great, unless one of you can come up with a better solution, but it has strategic, but which you can control. If you want less security, then you can have that security and performance trade off. But what we are able to achieve here is basically basically what you are able to achieve here is so as I said, the performance improvement is very tiny with 64 bit, but what we are able to achieve is the overhead. So, implementing AES and all that, and implementing chaffing and winnowing, there is a significant improvement both in area and power. That is basically the idea. So, it is not free, it is still lot of hardware, lot of thing, and so if you are working in this domain, you want to do that. The performance and delay number you directly get from GEM 5. When you run in GEM 5 simulator, it dumps the data, you look at that data, you get the value. To get these numbers, you have to write your design in VHDL or Verilog, use for example, Synopsys design compiler, compile it, synthesize it, and then the design compiler will give you those numbers, generate that area report, power report, and from that you get the number. So, you have to synthesize your AES 120 implementation that already exists in the community, then you can do this kind of stuff and so on and so forth. Any questions on encryption using chaffing and winnowing? Yes, please. Right. So, security comparison comes from the fact that chaffing and winnowing, all or nothing transform has some security guarantees, and that guarantee if it hold, then it would have comparable security to AES. But as you realize, when you implement and you do certain stuff, that kind of violates. So, AES is by itself. Here we have the vulnerabilities of the chaffing and winnowing and vulnerabilities of the all or nothing transform, both combined together, that may create some situation. But if we are building on top of all or nothing transform, if that guarantee is hold, so then it would be comparable to AES guarantee. Again, if you see the paper, it would have those guarantees discussed. So, the next thing I want to discuss about is called multicast authentication. Recall we are still discussing what kind of security enhancements we can do on the on-chip network, design for security solution. So, what is multicast authentication? Let me define the context first, then I will define the threat model. When a source is, again this is the actual, if you think of this as the CPU, this is the network interface, and you can think of either it is there or this is basically the router. So, every node has those three components, right. So, when source wants to talk to destination, this time they want to talk to multiple destinations. Can you tell me a scenario when somebody want to talk to multiple people? What are the context? Broadcasting a message. In programming paradigm, when do you broadcast a message? If you took computer architecture course, where did you see somebody broadcasting to somebody?
Routing, sir, we want to update the table and everybody wants to know the state of the table.
Right. So, you are right. So, let me draw something. So, this is P1, it has a cache L1, P2 it has a local cache L2, and they probably connected to main memory. In this context, think of at some point processor 1 wants to, let us think of a variable x with some location, let us say value 5. Processor 1 let us say wants to read that location x. So, x equal to value 5 comes in here, let us say 5 seconds later P2 wants to read it. So, x equal to 5 goes there, 3 seconds later P1 wants to write to it and changes it to 10. Now, because we use write back policy for performance, now we have a problem. This is you call as cache coherence problem. Everybody has their local data. If 3 seconds later P2 wants to read it again, it will say, oh, I have a heat here, it will read a value, but that is a wrong value, it should be reading 10. The way cache coherence protocol works, they maintain I am not going to get into the cache coherence architecture lecture today, but basically it maintains lot of table through Snoopy protocol or other protocols, directory based protocol, depending on whether it is a symmetric shared memory architecture or distributed architecture. But what will happen if somebody wants to write, it would inform on the bus, by the way I am writing to this address, everybody would be looking their location and they will invalidate it. The 5 will not become 0, but there is a block, invalidation block. like the way you have valid block, dirty block, there is a block that would mark as invalid. Now, this message of broadcasting that I am writing to 10 invalidate, in this example I talked about only 2 cores, it could be 32 cores. So, if somebody writing remaining 31 cores is getting that message, invalidation message. So, in this example I am informing 3 people, but cache invalidation depending on how many people have that data, it could be point to point, it could be broadcast, but multiple people are getting the same information. There are many such scenarios, but cache invalidation is one example I want to bring up to you, that if one party does something, lot of people need to be informed, same information. But for our discussion it is not important. Remember when you talked about garlic routing, it does not have to be exactly same message, right. It could be some of the path it is going through, maybe it is going here, maybe it is going there, but this path multiple people are going through. So, that is the idea of multicast authentication. So, what is the difference? Difference is, if multicast story or communication did not exist, how would you do the authentication or encryption for it? Let us say nobody knew about multicast, but this level of communication existed. What is the traditional solution that exists if you want to encrypt them or add authentication to them? Treat them as individual, do not treat them as 3 messages coming from same person, ignore that information. Just treat this color is going to this one as one color, treat this particular one as a different color, and treat this one as a different color. So, 3 different messages, it just coincidentally so happened source is same, ignore that, just encrypt them independently or add authentication independently. So, then that would be our, when you work, research or publish, you have to say what is the baseline, whom am I comparing with. So, our comparison is with, if we did not have this notion of multicast, we have unicast, single source, single destination, and we just treat those messages same message, but we basically treat them independently, create 3 copies of it, encrypt it, put authentication and send it out, AS to D1, AS to D2, AS to D3. That would be the expensive one. Can we do better? That is really what we are trying to solve. And why we need to solve that problem? Because here is the threat model, that although AS is sending information to D1, D2, D3, there might be a malicious node in the middle, this one, it might send invalidation messages pretending as S. If you send invalidation messages, what is the problem? Is that a problem? So, some data was in the cache, you are saying you need to invalidate because I am writing, but they are not writing, they simply want performance penalty. This is called performance degradation attack. Why? Because remember, if you send an invalidation message, that processor will mark that cache data as invalid. Next time it wants to read from the cache, that data does not exist. It has to go all the way to main memory, fetch the data, it is creating that cache miss, but in reality because this is a fake message, there is no invalidation. That data should have been valid, should have been in the cache, it should have took 1 cycle to read. So, this type of attack, not only it breaks authentication, somebody pretending as somebody, it also can lead to. So, remember we talked about the payload, it could be functional change, this particular case it is a parametric change like performance, it creates a performance overhead, which eventually can lead to denial of service attack. If performance overhead it creates so much, nobody else can get the service, it slow down so much, then it is a denial of service attack. Any questions? So, this is basically our threat model. Now, so the way we are kind of implementing, so there was a kind of a very lightweight hashing technique called CFAS. We basically tried to take advantage of it and try to come up with an idea. So, this case we are trying to solve the authentication problem. We could have treated it as a 3 different message and added message authentication code, each of them independently. Now, we are trying to construct one message authentication code for all 3 of them. And so, that is basically kind of we are doing not in a naive manner. Naive manner would be create 3 of them, put it in the same message. So, message part is not replicated, but 3 message authentication code are padded next to each other. When they change their path, let us say we are going together, oh this is already. So, let us say we are going in train together, then you are going to get down at your station and I have 3 gifts for 3 of you. When you are getting down in the station, I am going to give those gifts. So, if original thing created 3 MAC, the message authentication code 1, message authentication code 2, message authentication code 3, then when they separate out, here in addition to passing the message, I will give the message authentication code 1, because this is traveling together. And then here when it separate, I will pass here message authentication code 2, here I will give message authentication code 3, because this is where all the 3 got split. But this is kind of high overhead, because each message authentication code somewhere in the vicinity of 128 bits. So, then that is too much of overhead. So, we came up kind of created. So, we still want to maintain that level of information. You still have to maintain something and provide something, and how do you kind of optimize that, that is what we are trying to do, and opposite side you have the exactly inverse of that. So, what I wanted to show is basically because of this what kind of average packet latency, which kind of reflects what is the execution time compared to if you have no authentication at all, no authentication, they are just going and nobody cares. So, then whatever overhead would average packet latency would be, ours is this is 0.4, 0.5, this is 0.1, 0.05, 0.1. So, our one is lot of overhead compared to that, but it is significant less overhead if you do separate authentication for each of the packets. If you do unicast authentication for each of them, it is significantly. So, this is like kind of 90% from here to here. This is still lot of overhead, because this is 0.05 to 0.1, but that one is significant number. So, that similar trend kind of reflected in the total kind of execution time also. Any question on multicast authentication? So, what is the key idea? That a source will send the same message to multiple people. Do you want to have a separate authentication code for each of them, or can you do better than that? No questions? Okay, now I am going to talk about the last but one component. So, the first one is reconfigurable security. We have introduced so many ideas here, right. So, then on a network on chip, do you want to keep all of those security components, or do you want to reconfigure them, and why do you want to do, what is the context? You look at any system on chip device, it has, this is basically comes from the ARM little big design. So, ARM is the first company to show. Before ARM came in, everybody has an idea, if things are homogeneous, everything is equal, the performance would be nice, because then compiler can generate nicely, everything is equal. First ARM came in and showed, if you have one processor that is less powerful, less power hungry, another processor really power hungry, very fast, that kind of gives a nice overall kind of productivity. But anyway, so this is from that little core cluster, pictorially shown as small, and big core cluster and so on and so forth. And if we kind of plot, no matter what program you run, this particular case you have a display, memory, accelerator, and how they talk to each other. Depending on which program you are running, even within the same program, depending on what time you are looking at, the how many programs are active and how much time it is taking, how much resource utilization, memory utilization, these things goes up and down, it is not constant. It is not constant. And this would be easier to understand if you think about a program that is computing, let us say 2 for loop, even the same program. The amount of data you are loading may be too many array references, too many array references. This one maybe have no array reference or maybe just one. So, then the number of cache misses, cache hits that happens in this for loop is going to be significantly high compared to this for loop. So, if you look at a plot and look at kind of plot just kind of misses, you will have lot of misses followed by very little misses. So, there is all these kind of variations depending on the architecture, what is happening in a given specific time, there would be huge variations. And if there is so much of variation, same story holds even vulnerabilities. Amount of vulnerability that is out there when program is running, it changes. If you are using your phone in a coffee shop, that Wi-Fi versus if you are using Wi-Fi at your home, the level of vulnerability is different. Or maybe the amount of battery you have in your phone, maybe then you want to disable your security. So, if you do not have that feature, then it is not a great idea. So, reconfigurable security is good for anything. So, in this context we are talking about on chip requirements, because dynamic behavior, usage and all that changes. So, what we are trying to build here or what we build that architecture is basically a multi-tier kind of architecture. Some of the features we want to keep always on or maybe we turn on, and if you have more battery, if we think you do not feel safe, then you put one more tier on and then you make one more tier on. And what would be included the tier? We had a sample example, tier 1 should have bare minimum encryption, if every packet should be encrypted, encryption feature should be on, authentication if you want more, and then some runtime detection, that would be if you still have more or if you are still little worried, you are in a different country and whatever, then you might want to do that. There is even a easier solution than this, anybody knows when it comes to phone? You keep it off. People who are living comfortably the days there were no phones, what is the big deal, right? You can solve the problem at the root itself. Anyway, if we are not planning to solve that, what are the security primitive, what are the reconfigured parameters, this is just generally a general idea, and this is basically what we looked at, and we will probably have. But when you propose certain things, you have to propose it all the way. How in the system on chip fabric, how would it work? So, you need some kind of engine like the configurable security engine, different components would be there, whether that is a processor and analog to digital converter, controller, whatever it is, and there has to be some form of communication. That reconfigurable security engine is kind of maintaining the security policy. It has a lot of overhead, although it may not be obvious. The assumption is security engine kind of has directly or indirectly access to everybody. That is one. Second is, if security engine thinks display controller is doing funny stuff, so then it should have the ability to put some more restrictions or checks on the security controller, display controller, or whoever is talking to display controller. So, it is kind of not a very distributed parallel kind of story, it is kind of little bit of centralized and single point of failure problem. But anytime you use a security policy enforcement engine, you have to either you decide I do not want to do this, or if you want to do this, you have to take this overhead and this kind of trade off, unless one of you can come up with a better architecture. So, at the end of the day, in layman terms, what it is, if this is your network, think about it, this is your IP, let us say this is CPU, this is your memory, it will have its network interface and then the router. In the router, you have all these things that you can enable and disable, encryption, authentication, what is SAG? It does not matter, and then RRG. Never mind. So, all these kind of features, this is definitely denial of service attack. You will have all these features that you can turn on, that you can turn off. When packets are flying through the router, you can enable those security checks or you can disable the security checks. That is kind of how you implement. Any questions on reconfigurable security? The final one I am going to talk about, going back to, remember we talked about security assertions and we talked about in general what security assertions are, and now I am going to apply this for verifying network on chip trust. So, basically you have all these techniques. First of all, if you do not have these techniques, you can still apply, and we are going to use it in two ways. If you recall our discussion on security assertion, this can be used two ways. Assertions are properties. So, you have to deal with two things. What are the properties you want to check, right, and how do you derive those, that, and once you have that, how do you want to use it, these properties. So, these properties you can use formal verification. If you have a model of the network on chip, you can formally verify those properties, or which would be similar to any design for that matter. Only difference is all these properties will have source, destination, communication and all that properties. If so, for example, by knowing the network on chip, if there is a request, next cycle there should be an acknowledgement. This x means next cycle. If you think it may take 2 cycle, you put 2x. So, it has to be specific to that network, request, acknowledgement, or if you want to check for authentication, correct implementation, nobody should be able to figure out breakage. So, you can spell that out and complicated properties. You can do formal verification, that you can guarantee that design has no flaws for that property, or if you are not able to verify, then you put in the design itself, let us say VHDL Verilog code, C code, you put that as a assert statement, and all that complex equation you put that in the assert statement. During runtime it would check did the assertion violate, or you do both, that is the thing. Now, so how would then it work? So, basically the way it would work is that you need to have some kind of threat model. What are the threats we are looking for? Authentication, then the eavesdropping attack, then all of that stuff, anonymity attack. We will talk about a lot more attack in the afternoon. You already know what type of attacks are possible, and you are generating those kind of assertions. And when you generate those assertions, this is your network on chip design, it could be VHDL Verilog model, and when assertions are generated, you put those assertions there, and then you can kind of this is kind of the pre-silicon before fabrication. After fabrication, you can this assertion, if you want to map it to post silicon, those would be the trigger or the checker, hardware checker. And so, you will have design and tracing and hardware checker, and it would work. Now, let me give little bit of perspective on the post silicon, because this may not be clear. Let us say your assert statement is assert A, it does not matter what A is. In general, this expression is a lot more complicated. If it is a signal A you want to assert on, the assert function is a piece of hardware. How would assert work if it does not have access to that variable? Right. In your program you can say, well, I am putting this assert if file pointer and all that stuff, you are putting wherever you are opening the file. That is not hardware designed, right. You cannot, whenever you are computing a signal variable A, you cannot put a hardware there, right there, saying okay, now if it is failing just do it. So, you are putting that hardware somewhere else. So, you have to route that signal, or there is another choice, or there are trace signals or trace buffer. Remember, in the silicon you have billions of signal, and there is a buffer which stores some of them for little bit of cycle. There is a tiny buffer, 1024 cycles and maybe 128 signals. Those signal when you select, earlier our selection was for debuggability. You want to select the signals that helps you debug if anything goes wrong when it goes to the customer side. Now, your objective is, if you have any assertions, you want to maximize the visibility of those signals. You may not be able to trace A, but you want to trace somebody who can tell what is the value of A, you can derive value of A. So, then the lot of other subsequent functions will change if you want, when you consider the assertion and network on chip, and that is basically kind of, I believe that is all I want to talk about in verification. I did not want to show the properties and assertion, we already talked a whole day on this one. Any questions on verification of network on chip? That brings me to the end. We will meet after lunch at 2:30 p.m. Thank you.